introduce Max Engelstein, who's gonna speak about, from the University of Minnesota, who's gonna speak about winding for wave maps.
Thank you, Daniela. And thank you to all the organizers for inviting me. This is a really lovely opportunity to see some familiar faces, which is great because it's been a long time. Great, so I'll talk about winding for wave maps, and all this is joint work with Dana Mendelsohn, who's at the University of Chicago. And it's a little bit out of my wheelhouse, I would say. So I apologize upfront in advance if I don't cite your seminal work on the matter. I apologize, I'm still sort of a novice. But for those of you who work more in elliptic and the parabolic worlds, I hope to sort of show you an analogy between these sort of wave type equations and a phenomenon that we're a little bit more familiar with in the elliptic and parabolic setting. Okay, so right away, let me sort of try to convince you what the point of this talk is. That way you can run off and make a sandwich while your camera is off and you won't have missed anything. So what are wave maps? Essentially, they're wave equations with values in a manifold. So sort of like harmonic maps, but the domain is Lorentzian instead of having a Riemannian structure. And just like in harmonic maps, or really in any energy critical nonlinear equation, you can get energy concentration. And at these points in times where energy concentrates, if you rescale, you get a weak sequential limit, which will be a stationary object, a harmonic map or a bubble or a soliton. And the sort of fundamental question is, as usual, does this bubble depend on the sequence of rescalings that you took in this compactness argument? Or does it not matter how you rescale? You always get the same bubble at a particular point in time. So this is sort of an analog of uniqueness of blowups, but in the elliptic theory. And the sort of point of this talk and of the accompanying paper is to construct an example where you have non-uniqueness. You get different bubbles depending on how you zoom in at this point in time. And here we're inspired very much by a beautiful example from Peter Topping for harmonic map heat flow. But maybe one of the cautions I want to say is that the Hamiltonian or wave equation setup differs in very important ways from the parabolic setting. And I sort of want to highlight those differences here. So we weren't able to just sort of copy paste Topping's paper, although it was super inspiring to us. Oh, I should also say, in case it isn't clear, feel free to interrupt me at any point if you have any questions or anything like that. Okay, let me get into the beef here. So what is a wave map? It goes from R1 plus D, where 1 is the time and D is space, to your manifold. And it's the critical points of this Lagrangian. And what's key to note here is that the Lagrangian is not coercive, right? It has this negative sign. Maybe I'll draw the little negative sign here. And this lack of coercivity will have big implications, especially for those of you who are used to living in the sort of elliptic world. So what's the basic existence theory? You can prescribe initial conditions, and if the initial data is in C infinity, then the solution will exist, at least for a short time. The solution will also exist for rougher initial data for short time, but this is sort of a very complicated theory which uses a lot of high-level harmonic analysis due to Kleinerman and Selberg and Kleinerman and Macchiadon. For us, our initial conditions will be C infinity, so you don't need to worry about complicated harmonic analysis here. You can write the equation out in coordinates. I don't know how helpful that is to you. These are the Christoffel symbols of the manifold M. And so let me point out that if you only care about this Laplacian on the left-hand side, you get a harmonic map. And if you take just one derivative in time, you get harmonic map heat flow.
Max, can I ask a question?
Oh yeah, Francesco.
A really basic thing. So the M is a standard Riemannian manifold with metric G?
Mm-hmm.
Okay. Because you mentioned Lorentzian metrics, so but it's like R1 plus D as a Lorentzian structure, and then it's M is just a regular manifold.
Yes, you're absolutely right. I wasn't very clear on that.
Okay.
Yeah, so here the metric G from M, and then this negative sign corresponds to the Lorentzian structure in the domain.
I see. Okay. So,
Yeah.
okay, that's perfectly clear now. Thank you.
Okay, thanks. Yeah. So yeah, that's exactly right. And so this sort of, you can think of this as the Laplacian, if you'd like, this whole left-hand side as a Laplacian in the Lorentzian manifold on the domain. So this is sort of this harmonic map analogy. And so why would you study these things? Well, there's a variety of reasons. They have nice geometric applications, nice applications to physics. In general, they're just a pretty natural geometric flow. And so you hope that studying them and understanding them can give you similar geometric insights to, for example, the more recent insights we've gotten from mean curvature flow. So this is sort of the long-term goal. So I want to concentrate to a very specific, important example, which hopefully will help things be a little bit more hands-on. So here the target is a sphere and the domain is two-dimensional. And then the Christoffel symbols simplify and your equation looks something like this. And we're going to make an additional symmetry assumption, which is that the rotation invariance of both the domain and the range is sort of respected by the map. And under this additional symmetry assumption, the equations are even more simplified. And so let me draw you what I mean. So here is your domain, which is a plane. And here is your range, which is a sphere. Oh, everyone's in luck. This is the best drawing of a sphere I've ever done in my entire life. And what the equivariance assumption means is that we're basically just wrapping the domain around the sphere in this way, right? So the theta doesn't change. And as you go outwards, it's just this angle, alpha, which is changing, right? And so this angle is theta. So hopefully the notation here and the geometric picture is kind of clear. Okay. So we're restricting to this equivariant case. We have our example of the sphere, and there's a particular map which satisfies this equation, which is time independent, and it's the harmonic map. You can just believe me that it satisfies this equation, or if you've done work with harmonic maps, you know this very well, because it's actually a very specific and natural family of harmonic maps to consider from the plane to the sphere. In particular, it includes the least energy non-constant harmonic map from the plane to the sphere. And so what's really, really cool is that you can see this harmonic map as the infinitesimal behavior of a wave map, and not of a wave map which is stationary for all times, but of a wave map that definitely does depend on time. So there's this beautiful paper of Krieger, Schlag, and Tataru in 2008, which constructed an equivariant wave map, so one that has this symmetry, such that as time goes to zero, they like time going to zero as opposed to time going to infinity. I'm not sure why. The wave map splits up into a rescaled copy of your harmonic map, plus some sort of error term. And by error, what I mean is that in small neighborhoods around zero, the energy of phi, whatever that means, goes to zero. So what you can see here is that in an epsilon neighborhood of the origin, our wave map immediately wraps all the way around the sphere for t, which is really, really close to zero. So you're sort of having a breakdown of smoothness in some sense. A lot of energy, which is coming from Q, is concentrating in a very small neighborhood of the origin. And we'll make that precise exactly on the next slide. This phenomenon is known as blow up or bubbling, and similar phenomenon was constructed by Raphael Rodniansky and Rodniansky disturbance. Oh, hi, Inwan.
Yeah, hi. Can I ask you, so this power nu, is that something uniform or?
The powers nu which you can get is actually a really, really important question and basically completely wide open. So the rate of concentration is very much related to the dynamics, and it is actually quite related to this phi here. And so there are some really nice recent results, but understanding this rigidity is a really huge open problem.
Okay, thanks.
Yeah.
And hello.
Hi, see you. Yeah. Yeah, I should just mention that there are examples in similar equations of this type of blow-up behavior by Raphael Rudniansky and Rudniansky-Sturbins. So just to say that it's not just this weird wave maps thing that exhibits this, but a whole host of nonlinear wave type equations. So let me make precise what I mean by energy. I've told you that this is a Hamiltonian equation, so there should be a Hamiltonian, right? Like a conserved energy. And indeed, you can sort of think of it as being like a potential energy plus a kinetic energy. So it's easy to see, at least formally, just by differentiating this, that this energy is constant in T for any wave map. And also by doing a rescaling, you can see that if uxt is a wave map, then this rescaling is also a wave map, and the energy rescales in this way. So in particular, when d equals 2, rescaling your wave map keeps you invariant in terms of energy. And so now you can see why you should expect blow up to happen, because the only obstruction to blow up might be this sort of conservation of energy, right? But if you can rescale your map and concentrate the energy at arbitrary scales without destroying conservation of energy, then you might expect this to actually happen in the flow. And that's what's happening in the Krieger-Schlage-Tataru example. So in particular, this family, right, Q lambda, which was what, 2 arctan of lambda r, all of these have the same energy. This is the energy of Q lambda on R2, right? Here's the integrating factor, and it's radial. So in particular, what happens with this Krieger-Schlage-Tataru example, right? This is KST 08, is that in an arbitrarily small neighborhood of the origin, you still get a positive definite amount of energy as time goes to 0, right? So if you draw this little light cone, and we'll talk about what I mean by light cone here. So here's 0, here's x less than t, you get energy concentration at the tip of this light cone. And it turns out that this is somehow the only obstruction to global smoothness of wave maps. So either you get this type of energy concentration, or you can extend your wave map globally smoothly. And this energy concentration is exactly what we're going to sort of be studying in this talk. So, okay, more examples of energy concentration. This type of concentration can happen at infinity as well. When it happens at infinity, we call this error term a scattering term or a radiation term, which comes from applications from physics. And the idea is that phi should satisfy some sort of linearized equation as time goes to infinity. And sort of this is to Inwan's question earlier, you can actually get a continuum of these rates of blowups, at least as time goes off to infinity. And this was constructed by Pillai, who is a recently graduated student of Tataru. It's a really beautiful paper. And there still is some interesting questions about the connection between lambda, the rate of concentration, and phi, the sort of radiation. You can also have 2 bubbles, which can happen at the same point in time. Jacek Gendry constructed 2 bubbles in a wave map equation into a sphere, happening at the origin and time going to infinity. The key thing to understand here is that these bubbles have to develop at non-interacting scales. And I'll tell you a little bit more about what that means in a couple minutes. But the idea is that if you zoom in to try to get one bubble in the weak limit, the other bubble will go away. Oh, this is left over from before. Don't care about this k=1 case. But I should say that there's also important work of Casey Rodriguez. And again, to Inwan's question, there's some rigidity in what the 2 scales have to be. And this is really beautiful work of Jacek and Andy Laurie recently. In all of these examples, what's happening? You rescale time and you rescale space And then you get a sequence which converges as the time goes up to the bubbling time to one of these harmonic maps, right? The ones that we saw a couple of days ago, right? So days ago. This is how COVID warps time a couple minutes ago, arctan of R. And so we call this process U bubbling off a Q. And in all of these, we were able to sort of get a continuous rescaling to work, right? Lambda here, for example, depends continuously on time. Francesco, do you have a question?
Yes, Max, I wanted to ask you, in this example where t goes to infinity, do you have in the limit an equipartition for the potential and the kinetic energy?
Yeah. Maybe this is an answer to your question. What you can show is that, so here you have a light cone going off to infinity. If you take any cone which is strictly inside the light cone, the kinetic energy vanishes and you're left only with potential energy inside that smaller cone. The kinetic energy then needs to exit the cone. Whether it's equipartitioned, I don't think you can say that. For example, the Krieger-Schlage-Tataru blowup happens where the energy of U is epsilon plus the energy of Q, which tells you that the kinetic energy coming from phi has to be like epsilon in the limit.
Okay. Okay. So these are like examples where all the energy eventually become potential energy somehow.
Essentially, yeah.
I see.
Yeah, that's right.
Thank you.
So let me try to make more precise what this energy concentration means. So this is a paraphrase of a very important theorem by Sturbatz and Tataru, and it says essentially the following. If you have a wave map, then at a particular point, either energy concentrates inside the light cone with a tip at that point, or you can continue this wave map smoothly in a neighborhood of that point. If you have energy concentration, then there exists a sequence of points, a sequence of times, and a sequence of scales, such that when you rescale your wave map, it converges, passing to a subsequential limit, in a weak sense, to a harmonic map from R2 to M, right? So in all the previous examples, we were able to find continuous times for which this limit happened, but Sturbatz and Tataru tells us that in general, we're only guaranteed a sequence of times. It's a compactness result. Don't worry too much about this Lorentz transform, but you can sort of understand, you should be able to see all the isometries of the domain inside of this statement. So you can translate the domain, you can scale the domain, and then there's a Lorentz transform of the domain which mixes up time and space. You might know it from general or special relativity. We won't consider translations and Lorentz transforms because we'll rule them out due to some symmetry constructions. There's also an infinite time version of this, which talks about the scattering phenomenon that I mentioned earlier. And so I'd like to draw you the picture. So what is the picture saying? It says, here's your point, x0, t0, and then here's your light cone. So either you can continue your flow smoothly through this point, or there's a sequence of times and a sequence of points such that if you zoom in at those times and points, I guess this is now the center, then what you get in the weak limit is a stationary object, is a harmonic map, right? And this can only occur when you have energy concentration, and it occurs exactly when you have energy concentration. So this is a really beautiful characterization. Here's the same theorem, still paraphrased, and I have a couple remarks about it. This theorem was originally really appreciated because it allows you to guarantee smoothness if somehow you can rule out the presence of bubbles. So if there's some topological or energy theoretic considerations that you have to rule out this bubbling, then you can guarantee that your wave map is always smooth. For example, when you're looking at harmonic maps from R2 to M, there's always a least energy, non-trivial harmonic map. This is due to Schoen-Uhlenbeck epsilon regularity theorem, for example. So if your wave map starts with energy less than the least energy harmonic map from R2 to M, then you'll never bubble in this way. And so you can guarantee that you're smooth for all time. Or if there's some topological reason why such harmonic maps don't exist, then you can also guarantee that you'll never bubble. And so you're smooth for all time. There's lots of really important work in this direction by Krieger, Schlag, Struve, Tau, and Tataru. We're going to ignore Lorentz transforms. I mentioned that earlier. And so here is what I want to talk about with the two bubbles. If you have two bubbles developing at a point, they have to develop at non-interacting scales. So if you can pick one Rn to get omega and a second Rn to get omega prime along the same sequence of times, then it must be the case that these two Rn's don't see each other, right? That their ratio goes to 0 or infinity as we approach the blow up time. Because in the weak limit, you only get out one harmonic map. You don't get out both harmonic maps. And it's a nonlinear problem. The sum of harmonic maps is not a harmonic map. And so the big question here is, does this omega depend on the sequence of times going up to your bubbling time? Or can you really increase this convergence to happen in a sort of continuous way, to not depend on the subsequence? But of course, as I just mentioned, this is hard, because how do you know that you've shown non-uniqueness versus you've picked bad sequences of rescalings and times so that you just saw two different bubbles which happened at the same point? So I don't think I'm explaining this very well, but somehow the idea here is that because you have multiple blowups happening at the same point at different scales, even formalizing what it means for blowups to be non-unique is actually kind of a difficult problem. However, this is something that people have formalized, and we'll sort of see an attempt at it on the next slide. So let me maybe move on to that, and then I can sort of answer any questions you might have about this sort of trickiness. So here is something which is quite different from, say, uniqueness of blowups in the elliptic setting, right? Where you don't have to worry about two different things developing at different times. But of course, this does exist in the harmonic map heat flow setting, for example. So sort of understanding these different behaviors at different scales is what led to what's called the Celothon Resolution conjecture. And this was sort of first formalized by physicists in the 1970s, and it has its origins in numerical experiments of Fermi Pasta Ulam from Los Alamos, and then work of Krzyzewski on KDV, so like water waves, in the 1960s. And I write the Celothon resolution conjecture here for wave maps, and I've written a simplified version. But basically it says the following. Imagine you have a wave map which exhibits energy concentration at the origin and at a time. Then, as you approach that time of energy concentration, you get a simplification, or a decoupling, if you will, where the wave map can be created as a superposition of rescaled harmonic maps, and the scales are completely disjoint. So what do I mean by this? I mean that lambda I over lambda j goes to 0 or infinity as t goes up to t naught. And then you get this other term, which is smooth at 0 t naught. And in fact, if t naught is equal to infinity, then this term sort of satisfies some sort of linearized equation. So if you think about it, this is an incredibly ambitious conjecture. It tells you that the behavior of these nonlinear objects actually simplify into basically a nonlinear part, which is stationary, and a linear part, which is time dependent. So the equation like decouples almost into a free wave equation, not quite, but like a linearized wave equation, plus basically the harmonic map equation. And there doesn't seem to be any reason why this should be the case. But it was sort of confirmed experimentally for a bunch of physically relevant nonlinear wave equations in the 50s and 60s. So yeah, I should say that there are analogs for lots of nonlinear wave type equations, KDV, This is where the terminology soliton comes from, because it's talking about water waves. Nonlinear Schrodinger, nonlinear wave equation, Yang-Mills, a whole host of others. This version is simplified. I'm not considering Lorentz transformations or translations of the domain, but I feel like it's complicated enough already. There's been a lot of work on this conjecture for wave maps. It's easier to establish this type of decomposition along a sequence of times. So now you're just sort of asking for lambda sub n as opposed to continuous functions. And then you're asking for this to hold along sequences of times t sub n going to t0. Proving continuous time soliton resolution, like what it looks like here, is much more difficult. And there's been some really beautiful recent work on the subject, but almost all of them require some sort of extra assumption on the energy of U to make sure that you don't have too many of these bubbles, essentially one or two of these bubbles. Because when you start getting more of those bubbles, the dynamics between them become really, really difficult to understand. So maybe I should pause here and see if there are any questions.
Hi, Max. So I'm enjoying a lot your talk. So I'm full of questions and remarks.
I appreciate it.
So actually, it's quite amazing. So because this conjecture, if you think about it, for the harmonic heat map flow, for the harmonic flow in manifolds, heat flow in manifolds. I got it. Or for the Yamabe flow on a manifold even, right? I mean, these kind of theorems it's Struve in the 80s and then in higher and higher generality. So this kind of quantization with bubbles plus a smooth object in the parabolic setting is quite somehow standard. I mean, well established as a theorem, I would say, right? So it's amazing that.
That's true up to subsequences. So if you have the lambda sub n and t sub n, then it's definitely true. But I think even for harmonic map heat flow into the sphere, you need additional assumptions to prove a true continuous in time resolution.
Okay. I see what you say. Okay, it's I agree with you. No. You're totally right. So even in the parabolic setting, it's kind of an established fact along sequences. And then, for example, when you study something like the Yamabe flow, you don't care because you can show eventually that there is no bubbling, and so you recover the full limit. I understand. Okay.
Yeah.
Okay.
But you're absolutely right, Francesco, that this is sort of the direction that we're going to go in. The elliptic and parabolic people have thought about this for a while, and so we're going to try to steal their ideas and techniques and try to prove similar ideas here. Yeah.
Okay, I like that. Thank you.
Yeah. Cool. Are there other questions? Okay. Maybe I should state my theorem. So I'll do that now. So here's the main theorem in a paper that I put up with Dan and Engelstein earlier this year. It shows that for a particular manifold, continuous in time soliton resolution fails. So we construct a symmetric, and I'll tell you what that means, wave map from R1+2 to this warped product manifold, which develops a continuum of different bubbles at the origin as t goes up to t max. So in particular, for which you cannot have a continuous time soliton resolution like we've written here. And here, in our situation, j is going to be equal to 1. So the point is that the one bubble depends on the sequence of times that you take, and there is no continuous function lambda. So this shows that full soliton resolution doesn't always hold. Of course, all the results up until now have really been looking at wave maps into spheres or into other very particular surfaces of revolution. Here we cheat, I don't know, because F is going to be really nasty. This proof gives a family of initial conditions for which this phenomenon will occur, but this family is of positive codimension. So it's not necessarily a stable situation, which is a little disappointing. It'd be kind of cool to show that you can get non-uniqueness in a stable way. And what do I mean by symmetric wave maps? Well, the wave map will have two components. The component into the sphere will be equivariant, right? This is the equivariance we've seen before. And the component into the torus will be radial. It will only depend on the radial direction. So, okay, it's not quite a radially symmetric wave map, nor is it an equivariant wave map, because the target is not a surface of revolution, but this is pretty restrictive in terms of symmetry. So I'm not cheating in the sense that I'm not using like some weird breakdown of symmetry to create this phenomenon. We're going to call this quasi-equivariant because we're not very creative. The energy of the map is going to be just above the smallest energy of a non-trivial quasi-equivariant harmonic map from R2 to N. So we're basically going to give ourselves just enough room that we can create a bubble, but no more room than that. This is sometimes called the ground state. I'm kind of abusing notation here because you usually call it the ground state without a symmetry assumption. So usually the smallest energy of a non-trivial harmonic map, no symmetry assumptions, is called the ground state. But here we'll work entirely in the symmetry class. So we'll use this terminology ground state. So again, this weird phenomenon is happening not because we have a bunch of bubbles which are like oddly switching places or developing at weird scales or something like that. There's just one bubble. It's just sort of moving around too quickly and it never settles somehow. Okay, so maybe I should pause and sort of ask if there are any questions here.
Can I ask a question?
Mm-hmm.
Okay, so here you said like your result implies the full soliton resolution does not always hold. But does this mean that the previous work by Koenig, Haojia, they says like up to a subsequence they can find this confirm the soliton conjunction themes? Does it imply that their result is kind of optimal?
Not quite. So the work of Carlos and Hao is into very particular targets. So into the sphere or other surfaces of revolution with specific constraints on the metric that sort of prevent the type of non-degeneracy that we're going to exploit here. And indeed, some of the other papers that I cited here below, so for example, this paper here basically turns Hao and Carlos's result into a continuous time result, as does some recent work of Jacek and Andy. But I think it does tell you that if you were going to try to prove something in greater generality, the best you could do would be a sequence of times things like in the form of what Hao and Carlos did. So it sort of tells you that there is a limit to like Hao and Carlos's methods, I think, are super general. And what this tells you, and you can imagine them working, for example, in manifolds of this type. And so what this result tells you is that you can't improve a result of that type on a manifold in general without additional assumptions.
Oh, okay, thank you, I see.
Yeah, thanks. Okay, so this is the result. Let's talk a little bit about how it works. We basically get the idea from a similar result by Peter Topping on harmonic map heat flow. So harmonic map heat flow is essentially the gradient flow of the Dirichlet energy. But of course, your functions U are constrained to live in a manifold. So as I was talking about before, it's a similar equation, but you just have one derivative in T as opposed to two. And in a very beautiful paper by Peter Topping from 2004, he showed that there exists a harmonic map heat flow, again from R2 into a very similar manifold to ours. The warping factor is a little bit different. And again, it develops a continuum of different bubbles at the origin as T goes up to T max. I want to say that this paper by Peter Topping actually does way more than we do. But I'll give ourselves some excuses later. He proves some very beautiful constraints on what T max has to be, like the actual time of bubbling and at the rate of bubbling, which is sort of related to the questions that Imran had earlier. We can't do anything like that here, and we'll talk sort of about the obstructions to that later. In turn, Peter Topping's construction is based very heavily on a paper by Brian White, which showed non-uniqueness of tangents for stationary harmonic maps. And in between was another very nice work of Peter Topping, which showed that the long time behavior, even in the absence of bubbling, can be non-unique for harmonic map heat flow. Yeah, as I said, Topping's paper is very impressive. He does a lot of really incredible quantitative work. And he comes up with this really beautiful idea for establishing non-uniqueness. Remember, I said earlier that even saying what does it mean to be non-unique in the potential presence of several bubbles is quite difficult. And so Peter Topping came up with a way to check non-uniqueness, which is known as winding. It sort of gives you a topological non-uniqueness, and we'll talk more about it in a second. So what's going on here? Why are people able to go from sequence of times to continuous time Celothon resolution for certain target manifolds, but not for other target manifolds? And this essentially is related to something known as the Voyage inequality. So for an analytic function from Rn to R, Voyage, who is a real algebraic geometer, showed that around every critical point of this analytic functional, there's a neighborhood and an exponent such that the growth of the function near the critical point bounds from below the growth of the gradient of the function. So as a corollary, this tells you the following thing. If you have a gradient flow, which is generated by an analytic function, if it's bounded as time goes to infinity, then the limit of the gradient flow must exist. So Voyage was a real algebraic geometer. And then this huge breakthrough occurred by Leon Simon, who realized that even though this is a finite dimensional inequality, you can prove infinite dimensional versions of it for some problems. And in particular, this has been used in many settings to show either uniqueness of tangent objects or uniqueness of long-term behaviors of flows to a lot of elliptic and parabolic problems. The Yamabe problem by Brendel, mean curvature flow by some really nice work of Otis Chodos and many of his collaborators, and Kolding and Minikotsi before that. Yeah, so these are really, really powerful objects. But they've only been used so far in the elliptic and parabolic setting. Sort of the other side of the coin is that if F is not analytic, but is only C infinity, then you can have behavior where you don't have a uniqueness of long-term behavior. And this happens when you have a C infinity function that vanishes to infinite order, that basically contradicts the Voyage inequality. So maybe I should go back. You should think of this gamma. Gamma is sort of equal to n over n minus 1, where n is the order of vanishing at x naught. And so if you vanish to infinite order, then this gamma splits or sort of shifts down to the 1 part of the range, and you don't get this corollary. So in particular, there's an example of a gradient flow, which is generated by something very similar to e the negative 1 over x, such that it's bounded as time goes to infinity, but there's no limit. These are sometimes called goat tracks. You could think of like a little goat, which is walking up a mountain, and this entire curve will be the limit set for this gradient flow. And so these examples lie at the heart of the papers of Brian White and Peter Topping that I talked about earlier. And it's also going to lie at the heart of our paper. Okay. I should now try to toot my own horn a little bit and at least tell you why this wasn't so easy as copy pasting Peter Topping's paper. And the problem is that you can't immediately port these sort of parabolic lessons about gradient flows to the Hamiltonian setting. So in particular, it's very easy to come up with Hamiltonian flows, which are bounded for all time and which are generated by an analytic function, but which don't have a unique limit as t goes to infinity. I've written one down for you. And indeed, your calculus students could have written this down for you. The other problem, of course, is that critical points are no longer barriers. So remember the GO track example, grad f equals 0 was the limit set for the flow. And indeed, the flow could never pass through this set because if it did, well, it just can't by the maximum principle, right? As soon as this sort of stationary solution exists, once you intersect it, you're sort of constrained to the stationary solution. But here you have no maximum principle because it's a Hamiltonian PDE or a wave equation type PDE. And so indeed, this is sort of the GO tracks example. If you take the parabolic flow here, all the points on the unit circle, which is the set of critical points, are limits as time goes to infinity. But if you take the Hamiltonian flow, you can get a bounded Hamiltonian flow, but where none of these points are limit points as time goes to infinity. So somehow the heat equation has two advantages over Hamiltonian equations. This first one has to do with energy. The heat equation has to eventually stop because it loses energy in the limit. Hamiltonian equations have a conserved energy. So this is sort of related to Francesco's question about the balancing from potential to kinetic. And then sort of relatedly, the presence of barriers for the heat equation, which just don't exist for the Hamiltonian equation. So for example, there is no Voyage inequality for Hamiltonian ODEs. You can't do anything, or there is no corollary of the Voyage inequality for Hamiltonian ODEs. Okay, so with this in mind, we're still going to push ahead and try to construct the target manifold. So I told you that it was a warped product manifold between the torus and the sphere. And so that means that the metric is this weird metric that I'll construct on the torus, and then the standard metric on the sphere times the C infinity warping factor. The weirdness doesn't, or the pathological behavior doesn't come from H, but you choose H analytic so that this curve is geodesic in the torus. So what does this curve look like? If this is W, oh no, I think I want, no, that's good. Yeah, this is W and this is Z, then this curve winds around a ton at the top and winds around a ton at the bottom, and then it's just sort of doing normal stuff in between. And we can pick an H such that this curve is geodesic. Note the curve isn't defined sort of at the bottom and at the top here, but that's okay. It doesn't need to be sort of globally defined. So as the picture that I just drew showed, this curve winds around the bottom of the torus infinitely many times as S goes to either plus infinity or minus infinity. And what you do is you pick F to constantly be parallel to gamma, and such that the minimum of F occurs on the level set that gamma winds around. And this is only possible because F is non-analytic. It looks a lot like these sort of GO track examples. You could show, using, for example, the corollary to Voyage inequality, that such an analytic F does not exist. And what's important is that we've constructed this so that this gamma, when you take its product with the sphere, lies totally geodesically within the entire manifold, which means that if you have a flow that starts inside of this manifold, it will stay inside of this manifold. So now you can kind of see the idea, right? We're back here. We have our thing that winds a ton around the bottom. And so we'll start our flow here and then sort of expect it to go around and around and around and around and around the drain. And as time goes to infinity, there won't be a unique limit because it will keep just spiraling around gamma over and over and over again. Topic's manifold was very similar, but with a couple of key technical differences that I'll talk about later. I guess I'm going to talk about them now. Topping was able to simplify this construction substantially because he had a maximum principle. So we only sort of cared what happened, let's say, near the bottom of the torus. We don't have a maximum principle. So it's possible that you can start near the bottom and then go up to the top and then go back down near the bottom. And so this created some technical problems with sort of making sure that nothing worrisome happened if you approached this curve W equals 0 from behind, so to speak. Okay, so let me try to sort of define a winding singularity. So Topping had this beautiful idea that topology could help you figure out when a bubble was non-unique. So we say that a singularity is winding if, when you lift it to the cover of the target, it has no convergent subsequence, right? So the idea is that if there existed a lambda t continuous such that ut lambda t r converged to w as t goes up to t max, then it must be the case that the lift of this map, ut lambda t r, sort of stays bounded in the universal cover, because the lift of the harmonic map is stationary, and so obviously it stays bounded. But what happens here is that if you have like a circle, then you could imagine sort of going back and forth, you can imagine whipping around over and over and over again. And if you just think about the times where you're close to this point, you have a convergent subsequence. But if you lift this to the universal cover, at those same times, you'll be here, and then here, and then here, and then here. And so you won't have a convergent subsequence. So this is somehow how you can capture non-uniqueness using this definition of winding. Of course, you won't capture every type of non-uniqueness using winding, but it's a kind of a cool way to formalize any type of non-uniqueness using winding. So sort of to Yifeng's question earlier, I should point out that all of the manifolds that, say, John Koenig consider, their target manifolds are always topologically trivial, or at least they're simply connected. So winding singularities can't occur on those manifolds because the universal cover is the manifold itself. Yeah, so as I explained, winding means non-uniqueness of the bubble tree. There's no continuous in time Celothon resolution. And so what we show is that if your bubble is of the form Z naught comma Q, where Q is our favorite bubble from before, then the singularity must be winding. And that kind of makes sense, right? Because you have to travel all the way along gamma. And indeed, you're sort of spiraling around the drain. And then there's this associated spherical copy. And so if in the limit you look like this point cross the sphere, well, then it must have been the case that at another sequence of times, you looked like this point cross the sphere, and also like this point cross the sphere, and also like this point cross the sphere. And so you can sort of see how you get non-uniqueness in that way. So maybe I'll just take a second if there are any questions here. Okay. I will just sort of sketch the proof in case you're interested. So as I mentioned before, you construct this manifold. You take smooth initial conditions, which lie inside of this totally geodesic submanifold. Again, there's this additional complication that you need to define everything globally because there's no maximum principle. You show that energy concentration must occur, and thus you're in the Sturbins-Detaru dichotomy setting of having a bubbling situation. And this involves some nice ideas which go back to Christodoulou and Tabla-Darzadeh. In a harmonic map heat flow, it's easier for Topping to show that energy concentration must occur due to topological constraints. We can't quite do that here. Then we show that the flow can't leave this geodesic without bubbling. Again, this is harder because we don't have barriers. And then finally, we're able to use energy considerations to show that any bubble that we get must be of this form. And here is where we use the things that we learned about F, in particular that F has an absolute minimum at W equals 0, which is going to force the bubble to sort of appear at W equals 0. And then we use the topology of gamma, as I talked about on the last slide, to show the singularity is winding and therefore non-unique. Okay, so I'm almost done. This is my last slide with content. If you'll allow me, let me sort of speculate a little bit about what you might be interested in next, or what I'm interested in next. So philosophically, the purpose of this project, when Dana and I started it, was to understand why it's hard to prove continuous in time soliton resolution when you're going into manifolds with less, that are more general than the sphere, or that when you're starting not inside a particular symmetry class. And one of the reasons why it's hard is exactly the possibility that you might have a continuous family of harmonic maps from one another from using energy considerations. And you can't quite have this continuum family when your target is, say, the sphere. This also brings up something interesting. You know, I gave you this whole slide about why you can't just take elliptic and parabolic lessons and apply them to wave maps, but there's this beautiful work of Grinnis, which was able to use some harmonic theory to discuss wave maps into the sphere. This work, Tristan Riviere and Fang-Hua Lin, he applied to the wave map setting. And somehow there's this general moral that if you're inside a light cone where concentration is happening, then the dynamics inside this light cone are actually governed by elliptic or parabolic theory. And so we sort of consider our paper to be in the same vein. I don't think it's quite as impressive as Grinnis's paper, but it sort of is pushing the same philosophy, that elliptic and parabolic things can actually tell you quite a bit inside of the light cone when energy concentration is happening. One thing which really bothers me is the sort of physicality of this result, right? You don't think of non-uniqueness as being physically relevant, but on the other hand, analyticity, which is what you might assume to rule out non-uniqueness, also doesn't feel like a very physically relevant assumption. Like, I don't know how to tell if something is analytic in nature. Yeah, we're not sort of quite sure, like philosophically, where this fits in with the idea that wave maps should like somehow approximate something in nature. More concretely, sort of to my previous point, you might ask, are there examples where non-uniqueness is a generic property, even within a symmetry class? So maybe what's going on here is that non-uniqueness just never happens generically, and that's why you don't think of it as a physical phenomenon. You also might ask if you can get non-uniqueness not with one bubble sort of rotating around, but with two bubbles that sort of trade places in terms of the scales that they develop at over and over and over again. That would be kind of cool. And then, of course, you can ask the questions that Topping was able to answer in harmonic map heat flow, which is, can you get a rate on the bubbling, figuring out if there's a time by which this thing has to bubble. These types of questions, I think, are pretty fundamental and are quite important. Anyway, thank you so much for your attention. And that's all I've got.
Okay, thanks, Max, for the talk. Are there questions?
Sure, I have a very naive question. So I guess the role of harmonic maps seems pretty important in both the parabolic and the wave map settings. Is there any reason that you want to consider more time derivatives? dt to the k minus the Laplace?
Whoa, I have no idea.
There's some similar analysis.
I'm not sure. I think there are equations that involve a few more time derivatives that are studied, but I don't know if there's what type of methods are used and what type of physical phenomenon they model. So I really know almost nothing.
Just curious.
Yes. No, I think it's a good question. I'm really not sure. Yeah.
Okay, so when you say like the non-uniqueness, you're not sure whether this is genetic or not. When you say genetic, you mean the structure, it's with respect to the structure of the manifold or the structure of the PD itself?
These are, I mean, both, maybe, if I can have my cake and eat it too. I was thinking generic in terms of the initial conditions. So you fix a manifold and then let's say you do perturbations of the initial conditions, but keeping the symmetry class. So in our example with Dana, if you perturb the initial conditions off this geodesic, then you can't guarantee that you'll go back onto the geodesic. In fact, you won't. And so it seems unlikely that you'll have non-uniqueness if you bubble. But it'd be interesting to understand if you could cook something up where no matter where you start in the manifold, you always get non-unique bubbling. But I think questions like, what if you perturb the metric slightly? Or what if you add like a small error term into the equation? These are also really interesting questions, and I don't think anyone has really studied them.
Okay, thank you.
Mm-hmm.
Other questions?
Yes, I just want a very quick one. It's just about context. So are there similar conjectures for system that maybe have less of a geometric flavor, but more an applied one? Like, for example, I think you have hyperbolic systems with nonlinear constraints coming from elasticity. Have you ever seen anything like that? I'm not even sure if those systems are well studied at the level of existence and of solutions. So I'm really existence and uniqueness of solutions. So I'm really asking a science fiction question based on my knowledge. But if you've ever seen anything like that.
I haven't seen anything like that. I know that there's a little bit of debate within the community as to whether or not Celothon resolution should occur for like more nonlinear hyperbolic PDEs, like those coming from like gravitation and stuff like that. I think some people believe that this should still hold, and other people are a little bit more skeptical. But I'm not an expert, so I don't want to go out further on a limb there.
Okay. Thank you.
Yeah, thank you, Francesco.
Other questions? Okay, let's thank Max. And yeah, thanks, Max.
It's good to see you.
Yeah.
Thanks,
So I didn't
Max.
know you start doing hyperbolic things.
Well, I spent
You deserted. You deserted us. What are you doing?
It's only like a dalliance, you know, a small yeah, I spent a year in Chicago and all the cool kids were doing it. So I felt like I had to be I was forced into it. But I think in the end, I'd really like to understand the harmonic map heat flow better. It just seems like a very hard problem. So that was sort of the goal. Yeah. So I haven't completely abandoned you.
No, I know. You're just applying what you learned in other settings. Yeah.
Yeah.
So we are finally helping these poor dispersive people with some real insight. And this is recorded. That's okay.
Okay.
Thank you, Max. Bye.
Thank
Okay,
you.
so
Very nice talk.
I hope
Thank
to
you.
see everybody next week. Okay. Bye.
Thanks, Max.
Bye,
Great to
bye,
see you.
everyone.
Yeah, good to see everyone.